Hello everyone, hi and welcome you all on Physics Addhyan YouTube channel. So in this particular video, we are going to have a revision on thermodynamics and the upcoming 3 or 4 videos will be on the same topic. So in this particular video, we are trying to cover the important formulas that will be covering important formulas and important concepts, and in those formulas and concept we will solve some sample problems so that you can have a feeling that how to solve these problems using these formulas. And this, especially this revision courses, is important for jam and JEST examination that will be holding on 2020 January and February, mostly in February. And in the playlist in which you are watching this video, there are some other revision videos which I have made few days ago. That was on quantum mechanics. Few videos are on that, and there is a different playlist which is named as short tricks. So there will be some random videos on mechanics or quantum mechanics. So I will be having some short formula or some short method to solve a particular problem, which generally takes too much time. So using those tricks you can solve that problem in exam in very less time, so that time can be used to solve a different problem. So let's start with having a discussion on kinetic theory of gases. Okay, so when we study the kinetic theory of gases in thermodynamics, the first quantity will be deal is how what are the behaviors of that ideal gases in a container or in a closed box. So the first quantity that we calculate is what is the pressure exerted on the outside of that wall. So the pressure exerted come out to be in very simple formula. This is m into n by v into v square, that is average, where m is the mass of this individual gas, n is the total number of molecules of gas, and v is the volume. So this is the total mass. So this whole quantity can be written as capital M. This is the total mass. V can be written as total volume. So this is mass upon volume. So this you can denote as a density of gas. So this you can write density of gas, and v square average is nothing but you calculate the average of v all components. So this is v square average plus vy square average plus vz square average. So what does it mean? That you have n number of particles, you calculate the average of all the square of average of all the x component, y component, z component, and subsequently you add them, so you will get v square average. So this expression can also be written as half rho v square average. Okay, so this is the ideal pressure that is exerted on the wall of the surface. The second quantity which we calculate is, and in this particular course, we in the thermodynamics we define a quantity n that is called the moles. So moles is generally the number of particles divided by the Avogadro number. So if the Avogadro number and the number of particles are same, then the mole, which we call it as 1, and there is a constant, gas constant R, that is defined by Boltzmann constant multiplied by the Avogadro number. So R is a constant. In different unit system, the value will be different. So the second quantity which we talk about is average translational kinetic energy per molecule, AVERAGE, average kinetic energy of one molecule. If I talk about, so for one molecule, this the translational kinetic energy is nothing but 3 by 2 kBT. This is temperature dependent Boltzmann factor multiplied by the temperature. So this is for one molecule. If I talk about n number of particles, so this K translational will what will be just multiplied by n kBt into n. So this n I can replace it from over here. So n is equal to n into Na, and kb into Na will become small n, that is the moles. So this is 3 by 2 n RT. N RT. So this is for n number of molecules or n moles. So this is the average kinetic energy for n moles. For 1 mole, you can calculate n is equal to 1. So this is 3 by 2 RT, nothing. Okay, so this is the average kinetic energy of 1 mole or 1 per particle. Now there is a very specific calculations of having what is the average velocity, what is the mean velocity, what is the most probable velocity, and then the question asks that what is in 3 dimension, what its value in 2 dimension, what will be value in 1 dimension. So I will be having a chart so that you can revise all the important formulas at one place. Okay. Okay, so let us fill this gap. So this is, I will write here the dimension, in which dimension I'm calling. So let me first write it as 3 dimension. This is in 1 dimension, sorry, 2 dimension, and this is in 1 dimension. And the quantities over here is the root mean square velocity. This is V average velocity, and this is V most probable. Before filling this gap, let us see what this quantity means. So I have a distribution of velocity versus this probability. So we know that it is a Maxwell distribution in velocity. So the most probable speed is the maximum of this distribution. So this first is, okay, the first quantity, this was the most probable speed, and it is a speed that is possessed by maximum number of particles. Okay, so that is your V most probable speed. Then you have an average speed, so it resides something at larger velocity than the most mean, sorry, the most probable speed. So this second quantity is your mean speed, or you can write it as average speed. This is same as V average. And the third, which is the RMS, so average speed, that is what is the average of all the velocity speeds of all that particular statistical data which we have. And the third speed is something which is more greater than this, and that is called to be the VRMS. RMS is root mean square. So first you square them, then take the mean. So in this particular notation, you can find that this VRMS is greater than V average, and it's greater than V most probable. So most probable have the least number of magnitude in when I compare to these three. Now let's fill this gap and see how to remember it. So remember, there is a factor under root kbt by m which will be common in all. Okay, so I will first write this factor in all. So this is kbt by m. So here it is. Now let's me fill this gap. So these are numbers, you just have to remember these numbers. So this is 3, this is 8 by pi, this is 2, and this 2 comes over here again. This is pi by 2, and this 2, then it will become 1. This 1 will come over here, and this is 1 by 2 pi, and this will be 1 minus 1, that is 0. So this whole box is 0. Okay, so you just have to remember the number 3, 8 by pi, then 2 comes over here, pi by 2, then 1, this 1 comes over here, 1 by 2 pi, then 0. And the difference between this VRMS and VMP, there will be one order of, like square root of one order of magnitude. So this is 3, 2, 2, 1, 1, 0. Okay, so you just have to revise the average one, that is 8 by pi, pi by 2, and 1 by 2 pi. So this was the average mean speed, sorry, most probable, and the RMS value of speed at different dimensions. Now there is one more interesting quantity which we often deal while studying this gaseous system. So that is, what is a mean. We know that these particles collide with each other and have an average wave, the mean path. So what that mean path is, so let me call this as mean path, and what is also the time of that collision. So we will also discuss the collision time. So mean path lambda is defined by 1 by under root 2 pi over n into d square, where n here it is the particle density. So this is particle density, which you can write it as total number of particles divided by total volume. So this is particle density, and your d is nothing but, you can call it as diameter between center, or you can call that diameter of molecules. So this is diameter of molecule. We know that an expression for an ideal gas, that PV is Kb n multiplied by T. So from here we can find out this quantity n by V, n by V. So your lambda will be proportional to Kb T by under root 2 pi d square into the pressure. And this is a formula from which there were some problems on JAM exam. So you must revise this formula. And there is also a collision times which tells you what is the average time between any two successive collisions. So this is the collision time, and you get this collision times tau to be 1 by under root 2 pi n into d squared multiplied by the average velocity. So that is the collision time of for these gaseous particles. Now let us talk about the degrees of freedom and law of equipartitions of energies and how to calculate the specific heat, total energy and all that. So let me calculate, and this, remember, this is one of the most important topic for this particular chapter, because in any exam there will be given some vibrational degree of freedom, some translation, and you have to calculate the specific heat and all that. So in linear molecule, non-linear molecules, so you have to be very careful. So let's first find the degree of freedom of these molecules. So I will start with monoatomic. So generally the degree of freedom F, I write this is 3n minus C. N is the total number of atoms and C is the constraint that you have. Okay, so let me first write for monoatomic molecule. So for monoatomic molecule, your N is 1 and there is no constraint on that molecule. So C is 0. So your degree of freedom is 3, which is the translational degree of freedom. Okay, now let's go to diatomic. In diatomic there can be two cases, one it at high temperature and one can be at low temperature. Because at high temperature and low temperature the changes will be in the number of constraint. At high temperature whatever your bonding is, that can be break. Okay, so the degrees of freedom will increase. So let me start with the number n, that is n is equal to 2 in this case. So the number of constraint at high temperature is your 0. At low temperature there will be at least one constraint, that will be the bonding between these two molecules. So your F is equal to 6 here. Your F is equal to 3 into 2 6, 6 minus 1 is 5. So among these 6 there will be 3 translational and 3 rotational. Among these 5 there will be 3 translational and 2 rotational. Okay, so this was simple as that for diatomic molecule. Now let's move to triatomic molecule. So this is the third one. This is triatomic molecules. So in triatomic molecules there can be a further we can divide this. So one is linear and one is non-linear. What I mean by linear molecule is, let's say, see the example of CO2. So we have this kind of molecule of CO2. So that we call it as a linear molecule. And non-linear molecule, a very simple example, you can take an this H2. So there will be a lone pair. So this will bend this bonding. So it will be a non-linear triatomic molecule. So in both the cases, your N is equal to 3. If my N is equal to 3, and further there can be a description between these two, that is a low temperature and high temperature limit. Low temperature and high temperature. Okay, now at low temperature the number of constraints in this linear limit will be 2, and at high temperature it will be 0. So the total degrees of freedom is 3 to the 6. 3 that was 3n minus c. So 9 minus 2 is 7. This is 9. So out of these 7 there will be 3 translational, 2 rotational and 2 vibrational. Why 2 rotational, not 3 rotational? It is a different story. I will be dealing this is specific topic in detail when I will be teaching this thermodynamics particular video. So just for revision, there are two rotational and two vibrational. For 9, this is simple. 3 translational, 3, sorry, for linear, there will be always two rotations. So there is two rotation and four vibrational cases. Similarly, for this is there will be two limits, low temperature and high temperature. So for low temperature, again your constraint will be 3 because 1, 2 and the lone pair which is bending this constraint. So the total number of degrees of freedom is 6. Out of this 6, there will be 3 translational, 3 rotation and 0 vibrations, and here will be 0 constraints, so your degrees of freedom will be 9. So out of these 3 will be 3 translational, 3 rotational and 3 vibration. So this is how you can break a monatomic, diatomic and triatomic molecule in the number of degrees of freedom that you have, and then you can write the average energy of this molecule will be the translational multiplied by half kBt, because equipartition of energy tells you that the distribution of this energy is the total average kinetic energy is 3 by 2 kBt, and for each degree of freedom you have this half kBt distribution. So you have total number of degrees of freedom in translational with this translational energy plus vibrational with this vibrational energy. This is also half kBt, and here is a twist for, sorry, this was for sorry, this is for rotation. For vibrational there is a twist, there is no factor of half, it will be kb multiplied by 2. That is also a different story. Why it is not half, that is that I will be dealing in when I will talk that particular video in particular videos, the detailed videos. So you can calculate your specific heat to be the the temperature derivative of this average energy. Okay, so this is your specific heat of the system. So let us have a sample problem. So this problem is from JAM 2018 physics exam. So an ideal gas consists of three-dimensional polyatomic molecule. And this question I have just taken from this Physics Institute website so that I don't have to check it on official website. So this is three-dimensional and polyatomic molecule. The temperature is such that they have not specified whether temperature is low or high. They have just said the temperature is such that only one vibrational mode is excited. So the number of vibration degrees of freedom is 1. If R is a gas constant, then specific heat of constant volume of 1 mole, the gas at this temperature is the specific heat at constant volume. So you have to find the CV is what. If no information of this molecule or the temperature is given, then generally we take the a translational and to be the 3 degrees of freedom, and the vibration and the rotation to be the 3 degrees of freedom. Okay, because it is a polyatomic molecule, so we also can think that in it can have a 3 degrees of freedom in rotation and 3 degrees freedom in translation as usual. So the important thing when you calculate the average energy, so this is F translational, this is 3 into half kBt plus the rotation part 3 into half kBt plus the vibration part is important 1 into kBt. If you did half kBt, so this will be 3 by 2, 3 by 2, 3 by 2. So this will be 336 and 7 by 2. So this you can easily take this answer, but this is wrong. They specifically ask this question to know that whether you know this half factor is missing over here. So this is 336 by 2, this is 4 kBt. So the average energy is 4 kBt. So your CV is del E by del T average of this. So this will be 4 kb. I am writing in terms of kb, but there is given R is a gas constant, so one molecule of gas is given, so you can multiply this by 1 mole and you will get this 4R to be the answer. So this is the answer is 4R. So remember this idea that the vibrational degree of freedom has the distribution of kbt, not the half kbt. Now, let me have one more discussion on the specific heat. The specific heat, you all know this formula, that's why I'm going very quick. Specific heat is CV, that is du by dt, where u is the total internal energy, V at constant volume, and there is one more dependent on this energy, that is Cp. This is at constant volume, that is at constant pressure, and there is a relation Cp is equal to Cv plus R, or Cp minus Cv is R. Your there is a factor that is called gamma. This is Cp by Cv, and your gamma in terms of degree of freedom is 1 plus 2 by F. Your F is the total degrees of freedom of the system. If I calculate the speed of sound, so speed of sound, it generally comes out to be, this velocity of sound is under root gamma times the pressure and the density of the system, and your gamma is your Cp by Cv. So the speed of the sound is depends upon in which medium it is flowing, what is whether the gas is monatomic, diatomic, or triatomic. So it depends upon. Okay, you can write this P by gamma in terms of RT and the mass, then you will find out this is gamma RT by the mass. Okay, now if I have a question that if I have a monoatomic gas and a diatomic gas at the same temperature, which has some different mass ratio Ma and Nb that is given, then find the ratio of this velocity. So you can just have to use this formula, and you can generally get the answer. Okay, and one more thing, this temperature, you should convert this temperature into Kelvin. That's very important. That is generally they give in centigrade, so you have to add 273.15 to, or just add 273 to get in Kelvin. Then you do all the calculations. Now, two more quantities, and you all know the first is specific heat. Specific heat is defined as, let me be specific, that is the difference in specific heat. So this is delta Q. The energy transfer is ms delta T. The heat transfer, it depends upon the temperature difference, the mass, and this S quantity is called the specific heat. So what I generally write is dq, that is ms dt, and this in terms of sign, because there is a very sign convention. If I take this dt to be greater than 0, it means temperature increasing, then you are adding the energy. So I will write dq to be delta q to be the greater than 0, so that is enters into the system. So this heat when enters into the system, it means dq is greater than 0, then it means it will raise the temperature. And the opposite case, when it is lower the temperature, then dq is less than 0, that it means heat leaves the system. And there is a very well predefined principle that is called the calorimetry, which states that for a given system the heat loss is always equal to heat gain. So we will be using this formula while we're solving the entropy and all these types of problems. So the heat loss is equal to the heat gain of the system. Okay, so in this particular video, we have I had tried to cover all the important topics for JAM and JEST, specifically for the topic that was the kinetic theory of gases, and I think this is more than enough if you revise all these concepts and have a fair knowledge of these equations, how to use it, what that specific means. Like we generally confuse in the notations in thermodynamics. So if you know all these formulas, I'm sure that you will be able to solve. If you have practiced earlier, then you will be able to solve these problems if asked in JAM or JEST exam. Now for the next video, the topic is, let me introduce the topic, that is the gas law or the thermodynamics. So I will start with the gas laws. I will briefly describing the gas laws and laws of thermodynamics. Laws of thermodynamics. Okay, so in the next topic I will be dealing this. Thank you, and if you like this video, give a thumb up, because that gives us a positive feeling that you are watching this video and you are liking the content that we provide. So give a thumb up, make sure to don't forget to comment in the video, and thank you.